So another inclined plane problem, and we've got friction going in all sorts of different directions according to the way that we intend to move the mass. So it's magical to me how the friction changes direction according to which way we want to move the object. Here we go. So the first thing we're going to do is to look at the diagram, and actually for this problem we've got different things going on in the different parts of the question, so we're going to need a diagram for each part of the question. So for part A, what does the diagram look like? Well, here we are, we've got the mass at rest, we've got the slope inclined at 8 degrees, coefficient of friction. And because the mass wants to slip down the plane, the friction is opposing that motion. The friction is parallel to the plane, but up the plane. We've got the weight of the object, 0.5 g, and we've got the normal reaction perpendicular to the plane. So what are we going to do first? Well, I suggest that resolving parallel to the plane would be a good idea. The normal reaction doesn't have a component parallel to the plane. The friction is already parallel to the plane, and then we've got the component of the weight parallel to the plane, which will be in that direction, and that's 0.5 g sine 8 degrees. So Fr minus 0.5 g sine 8 is 0 because mass times acceleration, resultant force equals mass times acceleration, the acceleration is 0. So the friction is 0.68 newtons up the slope. Not very much at all, but it's a very shallow slope. Okay, for part B now, we need a different diagram, because what we're trying to do now is we're trying to add an extra force to the mass, and we want to have the biggest force before the mass moves up the slope. So now what we've got is we've got this force trying to move the object up the slope, and now friction is opposing that force. The force wants to move the object up the slope. The normal reaction and the weight are still there. So what are we going to do now we've got the diagram? Well, let's resolve perpendicular to the plane to start with, and we've got no component perpendicular to the plane from either of these two because they're parallel to the plane. We've got the normal reaction, which is already perpendicular, and we've got the component of the weight perpendicular to the plane, which is 0.5 g cos 8 degrees. So then R minus 0.5 g cos 8 equals 0, and 0 acceleration, mass times acceleration. So that's tells us what R is, and we can also work out, we can state that the friction, because we want to find the greatest force, we want friction to be limiting, so this friction is going to be F max now, and F max is mu, which is 0.75, times R, which we've just worked out here. So we know what the value of the friction is now. So when we go ahead and resolve parallel to the plane, we've got the friction, which is parallel to the plane, the force and the friction, which are both parallel to the plane, and we've got the 0.5 g sine 8 degrees, which is also parallel to the plane. So F minus the friction minus the component of the weight parallel to the plane, that's the resultant force, equals mass times acceleration, which is 0. So then the force is the friction plus this component here. So a total of 4.32 newtons required just to, that's the maximum that we can apply before the mass moves up the plane. So that's part B completed. Let's have a look at part C now. The greatest force that can be applied to the mass down the slope. So now we're wanting to change the direction of that force. We need a new diagram. So now the friction has changed again. They've changed so that it's opposing the intended motion, which is moving down the slope. So we have got now a situation where when we resolve perpendicular to the plane, it's absolutely no difference to part B. So what we said for part B, perpendicular to the plane, is exactly the same as part C, because we have only changed the direction of the forces which are already parallel to the plane, so don't have any bearing on the perpendicular, resolving perpendicular. Friction is also limiting as well, as it was before. So now though, when we resolve parallel to the plane, we have Fr in this direction here minus the friction, minus the force, minus the coefficient, the component of this force, which is parallel to the plane, equals 0. So from that, F is 2.96. So a lot less force required to move the particle down the plane than there is to move it up the plane. So there we are.